Saxon Advanced Mathematics, Lesson 68. Hey, are you ready for a kind of fun and semi-weird lesson about something that we really haven't talked too much about? Parabolas. Parabolas are the shape that we get. I'm going to draw a few little ones here just to remind you of what they are. Parabolas are the shape of a quadratic function. We've seen them before, and we draw them kind of like this. They're a U shape that goes up infinitely. We've graphed them, right? We've done the whole completing the square thing, and we know that sometimes they're skinnier, right? They can be skinnier. Sometimes they're fatter, right? We've dealt with those. Sometimes they go upside down. We've dealt with those as well. And we know that they're all a variation of this function, right? They go skinnier if you multiply them by a whole number. They go fatter if you multiply them by a fraction. They go upside down if there's a negative sign in front of them. That we all know. But what we're going to talk about this time is something called the locus definition of a parabola. Locus definitions are always weird because they describe the shape in relation to parts of the picture. So let me draw you what the locus definition of a parabola is. Here we have our same Cartesian coordinate system. And we're going to draw the parabola in just a minute, but first I'm going to draw two other things. I'm going to draw a dot on the y-axis, and I'm going to call that the focus. And I'm going to draw a dashy line. We'll talk about where I chose to put these in a minute. A dashy line called the directrix. That sounds like a character out of Harry Potter. It's one of the Lestrange sisters. They're the directrix. The parabola that we draw, and I'm just slapping it in because this is an example. If you measure the distance from any point on the parabola to the focus and any point on the parabola to the directrix, mine doesn't look perfect, pretend it is, these two lengths will always be equal, okay? The distance from the focus to the parabola is equal to the distance from the directrix to the parabola. That is the locus definition of a parabola, okay? This is the function definition. This is the locus definition. Now, what about formulas? What we know is that y equals ax squared when the vertex is at 0, 0, okay? That's what we had here. We can put a number there that makes it fatter or skinnier, but this is the way the equation works when it's centered on the vertex. Okay? A, this number A, is equal to something we call 1 over 4p, and P equals the location of the focus. Right here. It'll always be on the y-axis like this, but we create this coefficient 1 over 4 times the location of the focus. So we would say the focus is at point 0, p, right? The second value just tells us where that is. And the directrix, oh, I've run out of room. I hate when this happens so much. I'm gonna copy these over on the next page so we have everything in one place, because these are all the formulas and bits we need to know. Y equals ax squared. That is the equation of a parabola when the vertex is at 0, 0. We are later going to adjust this so our vertex can float around. A equals 1 over 4p, where p is equal to the focus on the y-axis. I'm writing this slightly different than last time. I've changed my mind about how I want to say it. I know. The focus is at point 0p. And then the directrix is the line of y equals minus p. So the focus and the directrix are linked by this variable p, which will change from problem to problem, but they both are described in relationship to p. The overall formula, if we take this and put it into this, is that y equals 1 over 4p x squared. And again, this is when the vertex is at 0, 0. Later in the lesson, we're going to update this formula, make it a little more complicated when we want to shift the vertex off the origin. Okay, that's enough explaining. Let's do a problem. Ready? I have to find a problem. Find the coordinates of the focus and the equation of the directrix for the parabola y equals 1/7. No, 3/7. It's really hard to read. It's very teeny tiny. Okay. So, what do we know? Find the coordinates of the focus and the equation of the directrix for the parabola y equals 3/7 over x squared. Okay, and I'm going to write our goal over here. Find focus and directrix. Okay, how do we do that? We know that the focus equals P. Okay, so I'm writing this from our notes on the other page. The focus is at 0p, and the directrix is at y equals minus p. So somehow we have to figure out what the value of p is in this equation. We know that this part is called a, right? It's the bit in front of the x squared. And we also said that that coefficient a equals 1 over 4p. Aha! So we can take the 3/7, plug it in here, solve this for p, and then we'll have all the information we need. So 3/7 equals a equals 1 over 4p, so we can write 3/7 equals 1 over 4p. The p is in the denominator. That's kind of weird, but it's not a floating p, it's down in the denominator. So let me just point that out to you. Okay, did John want us to draw this? He doesn't, but we can draw it anyway. Okay, so now all we have to do is solve this. We'll cross multiply, and we get 12p equals 7, and then we'll divide by 12. So p equals 7 over 12. That means the focus is at 0 and 7 over 12. Ew, that's not very fun to graph. And the directrix is at y equals minus 7 over 12. So these are the answers John wanted us to find. I'm just checking. Yep, that's exactly how he wants them stated. The focus is written as a point, and the directrix is written as a little equation, y equals. Okay, now let's take this and just draw a little picture so you can see how that works. And I'm gonna make the scale on my picture real big. The vertex is here. I'm gonna call this 0.0712. Note that I'm not worrying about making a scale on this. And then the directrix is at y equals minus 7/12, so I'm making it the same distance away. And this is y equals minus 7 over 12. Now I'm not going to go to the trouble to calculate any points, I'm just sketching, but I know that my parabola fits like this. Okay, we'll do down facing in the next problem, so you'll see what that looks like. Okay, so the focus is always on the inside of the parabola, and the directrix is outside the parabola, the same distance from the vertex as the focus, right? This is the focus, this point, and this line is the directrix. Okay, let's do another one. The focus of a parabola has the coordinates 0 and minus 5 over 3. And the vertex is at the origin. Okay, that's all we know right now, so that makes sense. Find the equation of the parabola and sketch it. Okay, we know that the focus is equal to 0p. We know that A equals 1 over 4p, and we know that the equation of a parabola is y equals a times x squared. Oh, so much beautiful knowledge in our brains. And we'll worry about the directrix in a minute. Okay, so what we need to do is we need to take this value for p, plug it into this, then we'll get the equation for the vertex. So A equals 1 over 4 times minus 5 over 3. Now I'm going to put that over a 1 so it looks better, all right? So this equals 1 over minus 20 over 3. Complex fraction, so I multiply both sides by the reciprocal. That will cancel, that will come out. A equals minus 3 over 20, because I'm going to need a negative, right, when I multiply by this reciprocal to make that into a positive one. All right. And we're supposed to find the equation. So the equation of this cute little guy is y equals minus 3 over 20 x squared. That's the first part. That's correct. Did I smiley face these numbers? I didn't. These are both right. Okay. It's not official until I smiley face them. Okay, so now we've got the equation of the parabola. Now John wants us to sketch it. Yes. Okay, So we know that P equals minus 5 over 3. All right. This tells us the focus, which is 0p, and the directrix, writing down formulas again, is y equals minus p. Oh, we're going to need that, aren't we? Okay. Picture time. The focus is minus 5/3. All right, I'm just going to call that minus 5 over 3. And that means we take the opposite of this number, and that is the directrix. So I'm going to go this way, and this is now going to be positive 5/3, and this is the directrix. What this tells us when we see that the focus is a negative number and it's down below, and the directrix is a positive number, and we still know that our origin is 0, 0, because that's all we know so far. This tells us that this is a downward facing parabola, because the focus is always inside the parabola. We would never have a parabola that goes toward the directrix and away from the focus. It always hugs the focus. That's how I remember it. They have a very fond and loving relationship, and the directrix is out of the parabola. That's kind of like the wicked neighbor. Okay, so that's how we know how to make it downward facing, is because our p-value, which drives both the focus and the directrix, is a negative number. So we go down to find it. All right, so this is the sketch of that parabola. Okay, so much for equations when the vertex is at 0, 0. Okay, now we're ready to level up. Let me tell you how many, oh, there's a lot to this lesson. There's only 4 examples, but they are just kind of heavy. Okay, so now we're going to take those formulas that we had and we're going to adjust them a little bit. All right, so now this is called a translated parabola, and our vertex is not at 0, 0 anymore. Our vertex is at HK, which are letters we've seen with relation to a circle, haven't we? So this is how it looks. Y minus K, adjusted for that, equals A times x minus h, adjusted for that, squared. Okay, that makes a certain amount of sense, right? Because this is where we are on the x-axis, so we adjust there. This is where we are on the y-axis, so we adjust there. Otherwise, it's just like what we had before. But we also know that A can be written in more detail, so let's just turbocharge this. A, we said, is 1 over 4p. There is the whole shooting match. That's all of our formulas we've studied so far in this lesson snowballed into one abominable snowman, I would say. When this is what we're using, our vertex equals HK. I already said that, but I'm saying it again, so this is all in one place. Our focus is equal to, because the focus will shift too, right? The focus isn't necessarily going to be right on that y-axis anymore because it goes through the middle of the parabola. And if the parabola is shifted, then that means the focus is shifted too. So the focus is at HK plus P. Okay, so we go to the center of the vertex and then we go up for whatever that amount P is. And then the directrix is equal to, I shouldn't put the equal sign there, y equals k minus P. Okay, so we go to the y value and then we go in the opposite direction. So this makes sense. Plus P for focus, minus P for directrix. There are the formulas that we're now going to use because we're now going to talk mostly about translated parabolas. P.S. If you just use these formulas and your vertex is at 0, 0, you'll still be fine because your adjustments will just be 0, right? So, honestly, we don't even have to think about those simpler forms of the equations anymore. We can focus on all of this. And this will work for anything. A parabola with its vertex at any point. All right, let's try one of these. Ready? My page is shifting, sorry. Probably looks like I'm falling off the table. All right, example 68.3. Ready? A parabola has a vertex of -2, 1. And a focus, I'm going to leave a little room between these because I'm going to write things underneath. The focus is -2, -1. Write the equation for the parabola, the directrix, and the axis of symmetry. Sketch. All right. The vertex we just said in our formulas is H and K. The focus we said is now H and K plus P. We can use this information to solve for those letters, and then we'll be able to create whatever John wants us to create. Okay, so what we know is H equals -2, K equals 1, and now we have to solve for P. We know that -1 equals K plus P, and we know that K equals 1, so I'm going to substitute that in. And so, we just do a little algebra. That cancels. -2 equals P. Whoops. P equals P. I mean, that's true too. It's just not very helpful. And then we know that the directrix is K minus P. One minus -2, right? Directrix is K minus P here. I'll write that here. K is 1, P is -2. We're subtracting, so that means it's equal to Y equals 3. Directrix we always write as a little equation, and I write everything else, vertex equals, focus equals, directrix equals, and then I remember I shouldn't put an equal sign there. Okay, my bad. All right, are we ready? We're supposed to write the equation of this parabola. So we know that that is that, okay? So all of this work we've done so far has been to get our variables straightened out, right? And now we're ready to actually do the equation. So it will be y minus 1 equals 1 over 4 times -2 times the quantity. I'm going to make a little box around this so my numbers don't overlap. X minus h, which is -2 squared. Now let's simplify. Y minus 1 equals minus 1 over 8. I'm bringing this minus sign out and multiplying minus 1 over 8 times the quantity x plus 2 squared. And now one last thing. You probably noticed this in our formulas. We write it like this so that we see the relationship between the k and the y and the h and the x. But when we're writing formally, I'm going to slide it up a little bit. When we're writing the equation of the line formally, what we want to do is we want to take this piece and bring it to the back, because we like to express our functions as just y equals. So I'm going to write it one more time. Y equals minus 1 over 8 times the quantity x plus 2 quantity squared plus 1. Change sides, change sign. So that minus 1 becomes a plus 1. That is the equation of the parabola with these values. Okay, I'm just double checking. Plus 1, perfect. The directrix we already figured out is, directrix is y equals 3, beautiful. And then what was the last thing? Oh, the axis of symmetry is just the line that goes down the middle. So it's the x equals. And our x value, we said, is minus 2, right? So we know that the axis of symmetry is x equals minus 2. This is correct, this is correct, and this is correct. Oh, I put the eyes and then I forgot to put the mouth. Double checking, minus 1/8. Yes, I hope you can see that. Way up at the top. All right. So that is how we can use this information. We have a bunch of little formulas and we have a lot of little values, but it's a fairly simple algebraic task to sort through and plug things in and create a beautiful equation. This moving the k is the last new thing that I just tacked onto this problem. All right, we have one more, and then we will be done. This problem, I'm going to readjust my book. I am sliding all over the place in this lesson. Okay. This kind of calculation lends itself very well to some fun word problems. If you have ever watched the James Bond movie, I always forget which one it is. There's a James Bond movie where he goes to, I think, Puerto Rico, and there's a giant satellite dish, and he's inside of it trying to get away from the bad guy, and they're running around in this giant satellite dish, and it's really, really cool. And that is what I always think of when I do this problem, because it's about a dish that could be a giant satellite dish. The reflecting surface of a parabolic antenna has the shape formed when a parabola is rotated about an axis of symmetry. What the actual heck are we talking about? John draws us a very nice picture, and I'm going to copy it into my book. Here is the same little business we've been looking at. This time, we have a flat, shallow parabola. Oh, that's sad. Pretend it's perfect. And it's an actual physical dish, but we're going to look at it. See, it's three-dimensional, but we're going to look at it as just a parabola, right? We don't have to take into account its 3D-ishness. The formula for this dish is y equals 1 over 20 x squared. Okay, this we know is a. We know that a is equal to 1 over 4p. We know that if we solve this, we'll be able to figure out the focus and the directrix because they both relate to p. Cool. It's rotated about its axis of symmetry, yeah, blah, blah, blah. If the measurements are in feet, how far from the vertex should the receiver be placed if it is to be at the focus? Okay, so this is a giant dish. This is the vertex here, and we're trying to figure out where the focus should be, roughly up there somewhere. Well, we know how to do that. This is the focus, right? This is a focus that is at the vertex, so I'm just going to use the simple version of our formulas, right? If we use the hard one, it would be H and K plus P, right? That's two ways we can find the focus, the simple and the suits all, the all-purpose. This one's got four-wheel drive. And then we know there's a directrix down here the same distance away. We don't care that much about that. John isn't asking about that. He wants us to find how far from the vertex should the receiver be placed if it is to be at the focus. So he's asking us to find this point because then that will give us that distance from 0. All right, this we can do. We know that this formula is going to help us change this number into finding what the p-value is. This equals A. So we're going to take these two things and put them together. 1 over 20 equals 1 over 4p. And I bet I don't even have to do the algebra. And you can see that p equals 5. Let's do it anyway, though. We'll cross multiply. 4p equals 20. P equals 5. That means our focus is at 0, 5. That means our directrix. John doesn't even ask about this, but we're just giving him all the details. This is at y equals minus 5, right? It's the opposite. And so that means that our, the receiver should be placed 5 feet above the vertex. That's the answer to our problem. The math was easy. Figuring out what the heck John was talking about, that was the hard part. Just imagine James Bond running around. I have to figure out which movie that is. I'm kind of into James Bond. They're a little dated. They're a little... James Bond's kind of a jerk. But they're fun movies in many ways. So that's what we've got here. This is the last problem. I just want to show you one last thing in the book that you don't have to worry about too much, all right? Those 4 examples cover everything you need to know. Remember that some of them are when the vertex is at 0 and some are when the vertex is not at 0. That has confused many a student. Why do I give you so many different formulas? That's why. In part D, which we're not going to cover, John goes through an explanation as to why the locus formula makes sense. This is called derivation, right? And what I want you to know is that it all has to do with the distance formula. And you can use the distance formula to calculate these two different distances, and it will all make sense that way. If you wake up screaming in the middle of the night because you don't understand why these locus definition formulas for parabolas work, then here's your answer. I don't need to put your brain through that. Okay, I believe that you trust me that these equations do work, but there's the proof. And again, it all boils down to our good old distance formula being put into good use. Okay, and you can see here, he goes through the work and there he gets y equals 1 over 4 p times x squared. Yay! Guess what? This very kooky little lesson is done. Thank you. Goodbye.